Welcome to today's TED Talk, right? Tech Talk, not TED Talk. Fiber optic cable selection. And we're coming to you live from the conference room here in Houston. And today, myself, Joe Belaski, be doing a majority of the presentation. Mike Masterson is here with me, socially distanced, of course, to help give any additional commentary or any places where I might be lacking or try to lead you astray. Just for everybody's knowledge, this meeting is being recorded. So, and if you have any questions, there is a question in chat section. I do have both of those windows open so we can try to respond as quick as possible. We do have a few upcoming events. We have a building faceplates in factory in FT View, ME and SE coming up for second week of March, and HART and highly integrated HART. We also have a users group, Scalable OE, coming up in March, and sadly we weren't able to do the networking update with Panduit on February 17th, so we are working on rescheduling that, and we'll have a date for that soon. So let's dig into it.
One thing, Joe, I will say, if you have any questions concerning it, please feel free to type them in and we'll answer them as we go.
And we were both monitoring the chat and the Q&A. So just let us know any questions. It's hard to have a conversation about fiber selection without talking a little bit about what fiber optics are and how fiber works. And in general, fiber is basically a concentric piece of glass. And we have a couple different densities of glass, and basically what they are is you have the glass down the center is what basically carries the light that you're after, and the glass around the outside has got a slightly different density, and so it has a different refraction rate, and that causes the light basically to bounce down the core glass down the center instead of just going out the sides. And that functionality is actually very strong and allows you to be able to go to corners and do other things like that. And outside of that, so when you look at, we've got a core, which is that high density piece, the cladding, which is a slightly different density, and then you have a coating, which is a protective piece around the outside. And so we make the minimum is 250 microns, which is still very, very small, like human hair small. And so we do make some fiber that has a 900 micron size to it, but basically that outer cladding is there to kind of protect it and to help kind of keep the light in and stuff as it's going down through. But in general, we're just trying to pass light from one place to the other and do it in a way where we can control it and get information through.
And what we were looking at that picture, that was a cross section of the actual glass, not the cable itself, but the actual fiber optic glass.
So this is an additional illustration where we have a little bit more about the different types in different sections. So when you look at multimode fiber, which is kind of one of the more common ones, it's got a larger core down the center, and it allows us to basically pass more diffuse light, and we use different optics to be able to run that. And typically LED driven is compared to the single mode, which is a much smaller. You see how small that dot is in the center, and that basically requires a laser to be able to hit that, so the light's going right down the core, down the center of it. Then when you look at the one on the left, you've got that 900 micron coating, which is basically the protective coating around the outside, the plastic coating that we use to be able to hold on to it and be able to see it. So we'll be able to look at that a little bit in a second. The main thing when you look at the different types of fiber, so there's two different main types, single mode versus multimode. So yeah, I think I'm gonna try to answer this one live. The single mode versus multimode. Basically, the differences of the core size on those, and that core size gives you a big difference in how the light travels through. And so with the larger core multi-mode, the light can bounce around as it's going through, which gives you some limitations that we're going to talk about. Where single mode, the light basically has to go right down the center because the core is so small that there really isn't the capability of the light bouncing around. Also, the use of lasers make sure that we can line up and go right down the center better as well. And where the multimode is typically LED, which is more of a diffuse type light. When it comes to multimode, there's a couple different types of multimode. So there's the stepped index versus the graded index. And basically it's how the core is built. So in the stepped index, the core is all one type of glass, where the graded you have multiple different types of glass. And really what that does for us is, in a stepped index, the light comes in and goes down every which direction down the center of this core. And so the light going right down the center gets there faster than the light that is bouncing from side to side, because the light going side to side has a longer distance to travel. So that's one of the the downside sometimes of multimode is, you get the stepped index, you can basically take this input pulse, and by the time it gets to the end, it looks different because you've now broadened it out because some of the light showed up before other light. And that kind of is one of the inherent limitations of the multimode fiber and how we set some of our length limits. And that's really kind of one of the main differences between choosing single mode and multimode. With the graded index, we get a similar functionality, but now because we've used different types of glass concentrically through that center, through the core, we can now slow the light down that's going right down the center and run and use a faster glass around the outside so that the pulse gets there more in time with itself. So you get less spread on that output pulse, which allows us to go with sometimes longer cable runs, because the further you go down this, the longer or the wider this pulse gets. And so you get to the point where you end up with pulses stacking on top of each other, not being able to tell when one is on and one is off. So when we talk about fiber optics, we're typically talking about light that is being passed down them. One of the worst things you can do with a fiber optic is look in the end of it if the other end is connected, because most of the time it does have light coming out of the end of it. You just don't see it. So one of the tests that we sometimes do on fiber optics is we take a flashlight, shine it from one end, and see if you get light out the other end, just to make sure it's not broken or something like that. But when you're actually have it hooked up, don't look in the end, because what you're looking at is infrared light. So there is light coming out, you just don't see it.
We don't want you to do it yourself LASIK surgery, because it's usually not successful.
Yeah, it's kind of pretty close to how LASIK works. So one thing you can look at is there are a couple different windows here that we look at in different frequencies. And so the wavelength is how we refer to the light in nanometers. And so there's a couple different wavelengths that are typically used. And so in single mode, we have the two wavelengths at the top, and in multi-mode, we have wavelengths just below that. And so those are the ones that are most commonly used. But on this slide, you can see that there's actually multiple different wavelengths that are available in different bands. And the attenuation is basically how far down, how long you can go before you end up with issues. So how much loss is there in the signal strength, or the strength of the light as it's running down the fiber. And this is actually a really good graphic to talk about some of the other applications for single mode fiber. And that is typically on the telecom side. In the industrial space, we typically use a dedicated fiber to transfer data one direction and then transfer data the other direction. We use dedicated fibers for that.
Transmit and a receive, basically, two fibers.
And in the telecom space, they typically will use one fiber and send a different wavelength of light each direction. And in some cases, they'll send multiple wavelengths of light down each direction, allowing you to basically do a multiplexing of multiple different pieces of light running down the same fiber in one direction and multiple coming back. The downside of that is the electronics on the end are very expensive, basically, to manage that, to read all those individual wavelengths of light and be able to manage that.
Currently in our industrial environment, we're not running into that. That's really more of a telco, regional operating utility type company that's doing that, utilizing that technology.
Right. And in that case, you're typically looking at a ridiculous amount of data being passed back through and trying to consolidate the amount of fiber because you're going over such long distances that the costs add up. So those are typically the reasons for that. But these other wavelengths do exist and they do work. So when you talk about attenuation, basically that's the decrease in optical power. So we measure that in dB, and that is affected by length. So that limits the distance, that how far we can go on glass. And then it also kind of sets some of the other pieces on how many corners and other things and how many connectors. When you go through connectors, you lose a little bit of light there. And so we get some of those losses there. And we typically have a budget on how much loss we can handle. So when you look at the total length of the fiber, the signal going in is a bunch of pulses, and coming out, you get the same pulses, maybe slightly more broadened out, but also shorter as far as amplitude. They're not quite as bright. And that is basically what our attenuation is, and that gives us how much loss we can accept. And I've got a slide coming up in a little bit that goes a little bit more into some of the limits on that. A couple other ways that we can lose some of the light is really sharp bends. So, as the reflection and refraction works with the light bouncing around inside of the fiber, if you bend it really sharp, really tightly, or a certain combination of bends, every time you do a bend, you risk losing a little bit of light from the core out to the product. And that results in some signal loss, or some amplitude loss.
And that comes down to installation practices. There are standards that are put together through groups like Dixie and some of the other regulations. Typically, your fiber, your bend radiuses will be 10 times the diameter of the fiber. That's what we want to do. And that's not really scary. You can still make pretty tight bends with it because these cables are very small. A typical 12-strand fiber optic type buffer cable is probably about 0.35 inches in diameter. So just take that into factor.
One of the other things that we look at is this dispersion. That was kind of what we talked about a little bit ago with as the light travels down, that it kind of gets there, some of it gets there fast and some of it gets there slow. And the longer your length of fiber is, the more these pulses overlap. So from the transmitter, you're basically looking at a square wave pulse. On, yes, there's light. Off, no, there isn't light. And doing that as quick as possible. And by the time you get to the end, you end up with these pulses that may overlap a little bit. So there's always some light, but it's not always at the peak intensity. And so we end up in this graphic here where we can have some pretty common situations inside of fiber systems where what we're sending top left is on, off, on, but what we get over at the receive end can be a variant based off of the amplitude. So if we have too much of this dispersion in that middle one, everything comes back and reads on, because even though the off in the middle was low, it was still above the threshold. It's too much light and it would reference is it on. And then you also have the other end of the spectrum, if we have too much dispersion and we throw a whole bunch of attenuation in there, and basically there isn't enough light ever to turn on for the receiver to receive it. And so that's one of the other common situations. Now there are ways to get with the excessive dispersion. You can do a little bit of additional attenuation, add some extra fiber in there to bring that signal amplitude down. But it's a balance between those. So typically, to avoid all this, we have some hard, fast rules on length limits and things like that, and that really kind of dictates which types of fiber we're going to use. So there's a nice standard out there where everybody refers to it as MICE, and basically it covers a whole bunch of different things to look at when you're selecting cable, and in our case fiber, looking at some of the different things like mechanical vibration, ingress of water, dust, climate, chemicals, electromagnetic. The main ones that we look at when we're playing with fiber is we really don't care about electromagnetic for the most part. We're typically going to be looking at stuff that's more climate and like water, dust, and maybe some vibration, but those are typically the ones that we're going to be looking at the most when it comes to fiber. And I liked this this chart, and we're only going to look at the two bottom elements on this: the copper versus fiber, multimode versus single mode. And this kind of dictates why we would use fiber, and kind of tells the story of when we would use which type of fiber. And in general, the benefits of fiber is you don't have any, you're optically isolated from one end to the other. And you don't have to worry about noise, you don't have to worry about running this right next to a VFD power cable. There's a lot of benefits there, but there's also an additional cost. Fiber is a little bit more expensive than a piece of Cat6 copper, but there's also some limits.
Actually not. Nowadays, if you take a look at the price of your Cat6, or especially your shielded Cat6 cables, you'll actually find the fiber optic cable is probably going to be less expensive.
There you go. So in some cases, it might be less expensive. Now, and the other end of it is most things come with an RJ45 port on them. They don't come with the SFP,
and that's the
added cost.
That's the electronics question.
So the electronics piece can add a little bit of cost there. So then that's one of the main things, and the other one is copper is a little less fragile than on fiber. When you look at multimode versus single mode, we're typically looking at distance. Distance is one of the main driving factors a lot of times in selecting single mode, but there's a bunch of other factors that go into it. Bandwidth is a huge thing. There are a lot of distance and bandwidth limitations with multimode. Where the higher you get to gigabit, you start really cutting your length down with multimode. And then there's also a difference in cost of fiber. So multimode, sometimes the fiber cost can actually be higher, but the electronics were typically cheaper. But it's getting to the point now that they're really fairly similar. The single mode equipment can sometimes not be that cost prohibitive, and the fiber itself is actually fairly cost effective.
Yeah, the rule of thumb these days is single mode fiber is actually less expensive than multimode. Fractionally, to tell you the truth, the cable doesn't cost a whole lot of money. It's the termination, it's putting everything together. But the single mode is always going to require you to use an SFP that is utilizing a laser, which is going to be more expensive than an LED. So the first question we had was, when do you choose? How do you choose multimode versus single mode? If I was building a new facility, I would probably, for my infrastructure, my outer ring or whatever, I would put a single mode fiber backbone in there. And eat the cost of the more expensive electronics, because you're future proofing your bandwidth availability. Because also with single mode, and we're not going to go into a lot of detail on it, you can do a lot more multiplexing over your two strands of fiber and get multiple signals over it. This is technology the phone companies use, but if you really want to truly future proof your plant, single mode is probably the better bet.
I agree. So when we talk about the different types of fiber, there's a couple different categories of fiber within multimode. And single mode, there's basically one. But the one piece you want to look at on this, for the most part, everything that we're doing new is going to be either OM3 or OM4. The main benefits there is when you get into the gig. So if you look at that last column on the right, the length limit is affected based off the quality of the fiber. And that's that dispersion we were talking about originally. And so when you get into some of these OM1s and OM2s, yeah, you can get your 2,000 meter with 100 meg, but when you get to that gig, your length is very much restricted. And at 500 meter length on gig for OM3 and 550 for OM4, they run very similarly there. So again, that's 1,500 feet, give or take, and that works pretty well for a lot of applications. Now, when you get into single mode, you'll notice that the number is the same for 100 meg or gig, and that's basically because there's very little dispersion in single mode. So with that, the limitation there of 10 kilometers isn't anything to do really with dispersion. It's more to do with attenuation. You just don't have enough light to, you can only the laser can only be so strong to go down it. So that's really one of the limits on the single mode when it comes to length, is typically the light.
And addressing the 50 micron multimode, The OM4 cable is backwards compatible to the OM3, OM2. Whenever you do your systems on your length, you're as good as your lowest common denominator. So if you have OM4 cable everywhere, but you're using OM2 patch cords, you would defer to the distance of your patch cords listed. So you'd be limited to, on a gig, 275 meters. Just keep that in mind. You can mix and match your 15 micron fiber. It's always best to know what you're using there, but you're usually good enough. If you don't know if your fiber's an OM3 or OM4, if you were to use the wrong 50 micron patch cord, you're probably not going to screw up your system. It's going to work just fine.
Yeah, so it's something to keep in mind and look at, but at the same time, it's probably not that big of a deal if you have the wrong one in this particular instance. So when we look at how the fiber is passed, when we look at a cable, we typically have a couple different types of cabling, and one of them is this tight buffered cable, where each one of our fibers has this 900 micron jacket on it that is basically melted and on it. It is its own piece. So when it comes out, it's all one, and it gives you something to work with there, because you have this ability to be able to individually terminate those when you look at a fiber. Where we also have this loose tube fiber, which is better for better pull strength, things like that, for being able to pull it through conduit, but it doesn't have that larger jacket. It's just the thermoplastic tube. And so when you want to deal with that, you have to do a fan out kit or something like that, because you can't basically put a termination on one of those. You have to do some sort of a splice to it.
Now, I will say, because we don't have, we didn't include, I don't think, a picture of the individual fiber. Your tight buffer is flexible like your typical Cat5 copper cable. Your loose tube will generally have a strength member in it, a dielectric strength member, which is like a fiberglass rod in the center, or AT&T used to put it on the outside of their cable. And that's for strength. The loose tube cable, that's what they typically use in the telephone industry. That has a pull rating of 600 pounds of tension on it, while your tight buffered cable is going to be rated for 250 to 300 pounds of pull tension. Because we don't have a strength member in a tight buffered cable, what we do have is some, if you've ever opened up one of those cables, you'll see some yellow material in there, and that's actually Kevlar. That's your strength member for these cables.
So moving on to the different types, so when you actually look at one of these cables, what does it look like? And so we have a few different ones here. We have our distribution fiber cable, which is, when you look at the cores coming out of that, those are going to be your tight buffered cable, most likely.
It is.
When you look at the IP rated one, you can see the cores actually coming out of those tubes. So that's going to be the loose tube style. So they're a little different there. But in general, what we have here is basically whether the cable's armored or not armored, and what type of armor do you have on it. And so when typically all of these cables we're going to be looking at for panel to panel interconnection, patch panel to patch panel interconnection. So that's where these are typically going to be used, where you're going to have to put terminations on the end of them once you get them there. There's benefits, like the armored fiber optic, gives you the ability to not require conduit. But we also have additional requirements sometimes with explosion proof environments and stuff, where we have to have a seal that can't just be a flexible individual piece. So
right, just going in a little bit more detail, going from left to right, the distribution fiber optic cable. This is a good slide. Mainly, one of the best things about it is that you see that cable is a teal color. I can tell you from my experience, that automatically tells me it's a OM3 or an OM4 50 micron cable. The one next to it being the loose tube cable, there's nothing you can tell without looking out of the outer jacket, except it's a loose tube cable. The yellow color coding for the armored fiber optic cable, the yellow tells me it's single mode. That is kind of a traditional standard, and the orange color, the one in the conduit, that tells me that's either OM1 62.5 micron fiber or OM250 micron fiber, which was an old military spec. So there is a color code. The only thing is, if you will see lots of cables that don't reflect any of these colors, that's where we have to read the jacket. And generally the jacket of any of these cables will tell us what we need to know.
And so when you're looking at these, there's a bunch of different standards and stuff as far as, you know, the different types of cables, how the jackets are, where you can use them in buildings and so on. And that may be a conversation for another day, because that in and of itself could be a half an hour talking about all those different standards. We're more focused on the fiber on the inside at this point. So anytime you're doing some of the loose tube stuff, you end up needing typically a fan out kit, where you basically have a splice in that connection in the middle, and it allows you to go out to individual connections from there. And so pretty much most of our suppliers produce these, and we have different variants of them, but it's an additional piece that needs to be done typically on a loose tube fiber.
Especially if you're doing direct termination, but it is very popular these days to do something called fusion splicing, where you're actually using a pigtail, which is basically, it's a fiber optic patch cord that's cut in half, and you're actually melting it to the glass of your, or the glass of the trunk cable that you pulled. This used to be a technology only phone companies used, but the cost of the fusion splicers have come down significantly, where lots of contractors do that, and it just gives you better repeatability when you ever try to terminate your fiber.
And when talking about terminations, we have a couple of the different connectors here that we typically see on the end of our fiber. The one that we use the most is going to be LC, because that is what our standard duplex style fiber is, and it fits. It's got a small form factor, so pretty much all of our SFPs, small form factor pluggable that plug into our switches. Those fiber optic connections are typically always LC. When you get back to patch panels, though, you can basically have any run of the ones that are up there, an SC or an ST connection as well. And then we also have off to the right some of the keyed LC connections, which basically allows, you know, you couldn't plug a blue LC into where an orange one was, because there's a little piece of plastic on them to keep you from accidentally plugging them into the wrong place. And most of our suppliers offer, pretty much everybody offers one of those, or a different type of those. So when you get into the patch panel, this is where you're going to be bringing in your bulk fiber in, and you can terminate it. And so on the right side, there's that light blue piece, which is where the fusion splices get mounted, that Mike was talking about. And then, you know, you can see on the left hand, that's a NEMA 3 box, which has the coil in it for you to bring in the fiber and wrap it around to have your service loop, and then go plug in. And you notice each of these boxes have one of these little pieces that we show in the middle, which is basically a connector on both ends. It's a board that's got double-sided connectors on it to connect your fiber on the one side, your bulk fiber, and then connect your patch cord on the other. And in some cases, what you'll see is in these patch panels, you'll see that, you know, you may have, you know, 6 fiber or something coming in, or 20 fibers, you know, a multiple of 6 typically. But you'll see a bunch of fiber coming in, and you know, you only use 2 or 3 of them locally, you know, or 2 or 4 fiber locally, and all the rest of them are basically patched through or fusion spliced through, and don't ever actually come out of the box and onto a separate destination. And so you typically daisy chain your fiber from location to location, as compared to doing, you know, home runs and direct runs.
And stay on this one just for a second, Joe. I want to point out, because I see a lot of fiber installations where people are just using basically a long patch cord going from A to B. And we'll get pushback sometimes saying, well, if I put a fiber enclosure or patch panel there, all I'm doing is degrading the system. Well, the cabling standards allow for this. Every time we make 2 fiber optic cables together, let's say like through one of these bulkhead connectors we see in one of these panels, we're going to estimate we're going to lose, I'll be conservative, like 1.5 dBs of power in our budget. And that's someone who does very sloppy work. You can do much better than that. But where I'm going with this is these patch panels are actually allowed to be put into the system. They're engineered into it. There's reasons why they're there. They will make your life easier down the road as you have to change your fiber network. And what you're seeing here are different examples. These things all come in rack mount, wall mount, or the one in the lower right is actually a DIN rail mount connector. So for any of our applications, we can put one of these enclosures in to suit whatever your application is.
And the benefit here is that it allows you also with the patching functionality to be able to pull multiple fiber from location to location. And then if for whatever reason you suspect one went bad or whatever, you can just move within the patch panel to a different fiber and it's already terminated there. You don't have to worry about having to pull another one. Yeah, there's a lot of benefits to going with this method. So in a standard application, this is kind of what we're looking at down at the bottom, where you have your local fiber, your local patch fiber running from like an ETAP to the patch panel, and then you have this permanent link running between your patch panels of your plant, which it could be from one side of the plant completely to the other. And then you have another patch cord basically on the other end connecting from that patch panel to a static switch or something like that. The direct patch method that Mike was talking about is basically where we just go buy a 2-core really long patch cord and pull that through the conduit, and you end up with just the 2 fiber, exactly what you need, and you're good to go. No additional permanent link, no additional terminations. You're turning a patch cord into a permanent link, and that typically works just fine for years and years until it doesn't. And then once it doesn't, it becomes a big deal because there's no additional fiber to use. There's no additional options. You're pretty well stuck and looking for getting another long patch fiber. So there are times where it is beneficial. Direct patch cables, especially within a panel, make 100% sense. But when you're going from panel to another, external from one panel to another, especially if it's a long distance away, it makes sense to do the backhaul, do that permanent link. So typically when we look at fiber, patch cable selection, we're looking at some of these limiting factors, and I know we're a couple minutes over, and bear with me, I think I can wrap this up before let's say 10:40. So there's a couple deciding factors when it comes to patch cable selection. Typically, first thing we look at, speed, 100 meg versus gig, length, how far are we trying to go, and then when we start looking at, is there an embedded SFP present? Because if there is, like in a ETAP or one of our other products, that really sets a lot of stuff for us. It sets the speed, it sets the wavelength of the light, it sets the fiber type typically, because it's already predetermined and you can't mix and match. So those things are typically what we use to determine, like, well, this has to be multimode. This, so that sets all of our other limits based on that. In cases where we need to go further or something like that, then an ETAP will let us. That's why we use a static switch with an SFP, where we can then switch over to single mode or something like that to be able to get that extra length, or to move to gigabit versus 100 meg. When you're looking at the backhaul fiber, or basically that permanent link, that's when you start looking at a few different pieces, because typically patch cables are used within one panel. So when you look at that permanent link, you're looking at, again, the same stuff initially: speed, length, and device limitations, which typically dictates multimode, single mode. That's the one that we typically look at there. And then you typically look at, is there already a fiber available in a patch, or being used in a patch panel, that you need to match to? And then you start looking at the environment that the fiber is going to pass through. Do I need to worry about class 1 div 1 environments? Do I need to worry about special chemical resistance? Do I need to worry about low halogen, low smoke, all these other things, because it's running through a residential environment or through a plenum area above something? Or those are all the times we start looking at that, and also looking at where the fiber is going to be run. Are you planning on running it in duct? We've got fiber duct, which is specific for fiber. It's not, versus are we doing a direct exposure, or we're just going to zip tie it to the ceiling? Zip tie the hopefully armored cable to the ceiling. And, so that there's a couple options there, but those are the pieces that we typically look at, and the questions we would ask you when you're saying, hey, we want a fiber, or I want to install fiber. Those are the pieces that are typically the most.
Or generally, if you ask us, what fiber do we need? These are all the questions we're going to ask you.
Yeah, so this is immediately what you're going to get back, is basically a list of these questions as we try to figure out what the limiting factor is to determine if there is one. If there isn't one, we're going to typically try to push you towards single mode, but it's one of those, if there is another limiting factor, we need to know that so that we select the right parts. So this is an example. So again, it's connecting from a ETAP to a static switch. The ETAP has a built-in SFP, so it is now dictating that we're going to use multimode. It's going to dictate that the patch cable needs to have an LC connection on it, because that's what the connector is on the ETAP. It's going to dictate the light because it uses 1310, and then it also is going to dictate the speed of 100 megabit. One thing that you can't do with fiber compared to copper is you can't mix and match speeds. There is no auto negotiate on a fiber system. There is auto negotiate on copper, but there is not on fiber. So you can't put a 1 gig SFP on the static switch and expect it to talk to 100 meg ETAP. It will not work. So at that point, you might as well be using a completely different thing where you basically have to match all of those additional must also match things under the SFP. If you get any of those wrong, you're not going to have a connection between the two. So it's very important to understand that. And then, selecting the fiber basically is what do I need for my end connections? What type of fiber do I need? And then in this case, multimode is enough. I don't need to really specify OM4, OM3, don't need to specify any of those others, just because it isn't interconnecting to any additional fiber, so it doesn't really matter. So the length limitation would be the one reason that you may need an OM3 or OM4. Typically, most people get that anyways. So we're not seeing a lot of OM1, OM2 on new applications. Similar example, but this time adding in that permanent backbone and a couple of patch panels. So now we have a few additional pieces we need to look at on trying to make this decision on what is going to limit us. So again, if I'm using an ETAP, that's still limiting my decision, and I have to go with multimode. I'm still using a 1310 nanometer, and I'm still using 100 megabit. Now, as far as the OM3, if my permanent link was an OM3, I should probably do my best to make sure that at least all my connections are OM3 or better. And same thing with my fiber. And then when it comes to the actual patch panels, you can use pretty much whatever connection you want. So I know on like my fibers, I'm showing I need an LC connection on the ETAP end or on the SFP end. On the other end, it could be an ST or whatever connection type you used for that cover in the patch panel. And the same thing for the backbone fiber. And so that's really some of the main stuff that we look at there when you're selecting these.
Yeah, I get asked a lot of times, well, what's the part number for the ST or ST version of an SFP? The answer is there is none. All SFPs are kind of standardized. If you notice, go between vendors, whether it's Cisco, Rockwell, any of the other switch manufacturers. SFPs are a uniform size because it's standardization. All 100 meg and 1 gig SFPs will always be LC connectors. All the transitions will be done via patch cord at the fiber box. So that's how you'd go back to your ST, SC, or FC physical plant. So biggest thing is don't get bothered by the fact is there are different types of connectors. There are ways we can approach it to make the transitions. We do it every day.
And one of the key things here is there are a couple manufacturers out there that do make some media converters and other stuff like that don't have LC connections on them that you can get with an ST connection on it, or you can get with an SC connection on it. And so it's important to understand the equipment on the end that you're trying to connect to see if it already has a physical connection requirement or a limit to make sure that when you're doing that patch cord that it comes with the right type. So in this case, if I was to change this ever so slightly and put a static switch on both sides, my multimode requirement would go away. And at this point, I could look at single mode, I could look at gig, I could look at different speeds. My LC requirement would still be there because I'm looking at SFP's connections, but I could look at different wavelengths of light. So at that point, we aren't limited there, and we'd start asking questions on, do we want to use multimode or single mode? And typically we would try to push towards single mode and transition over from there. So one of the last things I've got for you is typically, testing. Don't assume. When you put in new fiber, you want to test it, and once it's in and it's working, every now and then you may still want to test it just to see if it's degrading, because fiber does eventually degrade. It's not a fast degradation, but depending on the environment and stuff, sometimes it can be quicker than others. So it's important to do your test. And typically one of the first things you do is a visual with magnification, just to make sure that you have a clean cut on the fiber, that your optics are clean, that you don't have any issues there that you need to cut it again. So this time we're talking more about, the splicing and the connections. Then we typically do a visible light test, which will basically give you, the easiest one there is just a flashlight. Is there light? So it knows that you're looking at the right fiber. And then also that there's a true complete break in it somewhere. And then you do a loss measurement test to make sure that you're within that loss budget. And, in some cases we have SFPs that are stronger, especially on the single mode, to be able to go that longer distance to be able to handle that additional loss. So sometimes some of the single mode SFPs will have a length suggestion on them versus, two different types to be able to give you those different lengths. And then the last one is typically an OTDR, which gives you the ability to truly diagnose the fiber and say, okay, I'm good, or I have a little issue over here, or I have good signal strength, and I'm going to be able to get the speeds that I want and be able to certify, say, yes, this is going to work, as compared to, well, it should work. It's one of the biggest things when it comes to the copper side is I've got flashing lights, therefore it must be fine. That is one of the OTDR functionality, or being able to test your fiber to its full capacity is extremely important.
And OTDR is giving you a full snapshot of from point A to point B of everything that's going on in the fiber. It's cable radar. We can actually tell you where you might have micro bends in your fiber using that. Now in OTDR, it is the more expensive piece of equipment here, but I will say one thing: while it can give you the power, your power budget or your power loss, the power meter and light source, which is option number 3, is actually much more accurate at that. So the two go hand in hand. Those pieces of test equipment, it's nice to have both of them, given the option.
And so I'd like to take a moment and thank the guys that made this possible. I borrowed quite a few slides from AFL and our partners at Panduit, OCC, and Fluke Networks, and Rockwell and Cisco. Down at the bottom of this, and we'll make this slide deck available, there is a link to that PDF from Rockwell, which is a cable selection. I actually grabbed quite a few screenshots out of that as well. And it goes into a lot of detail about the different types of fiber and why you would select different ones versus in understanding the different uses and so on. So if there are any questions, I haven't seen but the one come in through the Q&A.
We do appreciate your time, and if you have any questions, if you want to do a deeper dive on what jacket I need for my cable in a certain environment, feel free to give us a call. We're pretty well versed on this, and we can generally get you set in the right direction. And with that, I guess we'll say thank you.
Thank you for coming.